Let me ask you something. What do you do when you own and drive a Ferrari and your car keeps breaking down and exhibits slow performance? This is what happened to Ferruccio, a tractor entrepreneur in Italy in 1960s who noticed that his Ferrari was too noisy and rough, and he also complained about a poor interior. Now, I know what you must all be thinking. What is a tractor entrepreneur doing criticizing a company like Ferrari? But let me ask you this. Did you ever own a vintage Ferrari 250 GT which kept breaking down every once in a while? I'm guessing the answer is no, but what if I was to tell you that Ferruccio was also a mechanic, tired of having to go to Maranello to get his Ferrari fixed every once in a while? And being a mechanic, he noticed that the clutch on his Ferrari was inferior and actually the same one he used for his tractors, which is why his Ferrari kept breaking down. He raised his concerns in Ferrari with Enzo, the CEO of Ferrari, but was met with indifference, saying that he should stick with tractors and he cannot handle a Ferrari car. This motivated Ferruccio to open a separate division for producing cars that are high-end with great performances. In it, he created the Miura, putting everything he wanted out of a car into it, including putting the engine in the back instead of in the front, and thus creating the first supercar ever. Ferruccio's last name was Lamborghini, and his company's legacy proved to be a meaningful one, producing high-end GT cars in the growing market for it. But what can we do as engineers and designers if our car is not performing well and suddenly stops in the middle of nowhere? Now, we can take complaining about our car and opening our own automobile company as plan B, but a plan can be to either call the tow company or roadside assistance and wait, or look under the hood and diagnose the problem. Is it the oil? Is it too low? Are you out of gas? Is the engine out of radiator fluid? Even though you may not know how to fix these things, you would probably want to know how to diagnose an issue to offer the best response in a timely manner. The same can be said for playing games, which include real-time rendering and graphics. You don't have to know about everything that happens under the hood, but you should know enough to diagnose the problem and offer solutions to optimize their performances. If an issue occurs like lagging or inability to display graphics properly, poor resolution, and non-immersive graphics, you need to know how the game is made and what is causing it. And this doesn't only mean talking about geometry, materials, and lighting as the three main components we mentioned in the past. So is there something that takes all of these components and uses them to create the images in real life for our specific platform and for our desired FPS? That is the graphics rendering pipeline, or the pipeline. And in this lecture, we are going to talk about what happens under the hood of real-time rendering, diagnosing, and optimizing the pipeline. So we can start with the pipeline and answer the question, what is the rendering pipeline? As we can see from the book Real-Time Rendering, the main function of the pipeline is to generate or render a two-dimensional image given a virtual camera, three-dimensional objects, light sources, and more. And given that it is a pipeline by default, it should be done in series or in parallel. From the image and the definition of a pipeline, it should be done in series, with each stage being dependent on the results of the previous stage. So let's take one example of stacking tiles for the Jenga tower. It is a game where you stack 3 tiles in each row, alternating their direction perpendicular to each other until you build a stack. And then you take turns taking off pieces of the stack to put back on the top, until an improper tile removal makes the tower collapse due to lack of stability or inadequate moves. Now, if we want to start the game again, we can stack the tiles quickly without aligning them. In this case, we prioritize the speed of initial stacking over proper tower stability. We can increase the speed of this process further by allowing multiple people to help out in stacking. However, if one person takes more time than the others to place the tile, we are losing time, which is where we introduce the concept of a bottleneck, which can represent a place where the road narrows, causing the traffic to slow down or stop, but in a more generalized meaning, it is something that slows or halts free movement and progress. If it can happen in a Jenga as part of an assembly pipeline, it can happen in multiple parts in the graphics rendering pipeline. So where do we get started? First, we can understand how the pipeline works and then diagnose the possible bottlenecks. So first thing to notice is that the general graphics rendering pipeline has 4 stages, which are the application stage, followed by the geometry processing stage, after which we can rasterize the geometry as pixels, and finally calculate the final color of the pixels based on all the data we have incorporated in the scene, like materials and lighting. We can see that some stages have several, sometimes optional substages that can be executed in series, like the geometry processing, or that can be done in parallel, like is the case with pixel processing. But we can start our exploration and comprehension of the rendering pipeline with the application stage. Now, the application stage is the environment where the foundational elements like the geometry and materials and lighting are all initially set up. As with all applications in software, it is run on the central processing unit or the CPU. But do we really know what a CPU is? Now, we all know that computers convert data into digital signals and perform mathematical operations on them. The CPU is the primary component that processes the signals and makes the computing possible. Now, CPU is like a large industrial pipe capable of performing any kind of task thrown its way, but it has to do it in series. And this enables the CPU to efficiently run the large variety of tasks that are responsibility of the application stage. Some of the tasks traditionally performed on the CPU include collision detection, global acceleration algorithms, animation, physics simulations, and many others. But instead of just one pipe, computers nowadays have several pipes called threads, and are hence capable of performing several times more information per second than the single CPU computers. So with a 12-thread 3 gigahertz CPU, this means that we can handle 36 billion pieces of information each second, which seems like a lot, but we have only gone through the first stage of the rendering pipeline. Next, we have to check out the geometry processing. Now, the geometry processing, as the name implies, deals with transforms or transformations, projections, and all other types of geometry handling, like transforming vertices and triangles on the view plane in reference to the camera. So since the smallest unit we can work with is a vertex, which is just a point defined by 3 coordinates, we can use it to generate lines and polygons that make out the geometry of our scene. Now, how much information can one vertex carry? Is it just the 3 coordinates, or can it carry anything else? Let's take a look at this data that exists for the vertex buffer. We can see that we can fit much more data than just the coordinates, including the normal vector in reference to the adjacent polygons, as well as the color or the UV information. Now, this stage is known as the input assembler, which sets the stage for the vertex shader. And the vertex shader is a small program that computes the position of a vertex, but can also pass existing data like UV coordinates and generate additional vertex data such as colors. However, all the position data has to be computed in reference to the camera or the view space. So how is this done? Simply by using various transformations. We can take the vertex coordinates in reference to the model space, then transform the coordinates in reference to the position and orientation of the model in the world space, transform it again in reference to the camera space, and then finally transform it into the view space, which is the projection on the screen that we see. However, before we transfer the vertex data to the view space, we can do several additional and optional steps. So we can go back to the camera space, which is basically just a truncated 4-sided pyramid that is enclosing a volume of space, which we call the viewing frustum. All the vertex data that are generated after the vertex shader are in a 2x2x2 space known as the canonical view volume, which can be done using 2 methods, which are the orthographic or the parallel projection and the perspective projection, which I believe we are all pretty familiar with. But if we are not, the orthographic projection has all the parallel lines in the scene appear parallel in the viewport as well. And this was used for older games where the performance was an issue and the 3D geometry had to be replaced with sprites or 2D cutouts. Whatever the case may be, we can still do some additional vertex processing in this stage by introducing the tessellation substage here. Now, the tessellation substage allows us to render curved surfaces. As the name implies, in this stage, we take the given vertices, but also the triangles they make, and add additional vertices and triangles in them, thus enhancing the number of vertices and details, as can be seen in the example of this Utah teapot. This does not mean that we are increasing the level of detail in the scene, but just allowing the displacement maps, for example, to be depicted in a much greater detail. The tessellation stage consists of the hull shader, which can take the triangles and pass them to the tessellator, which generates the adequate number of subtriangles in a specific configuration before handing it out to the domain shader, which creates the new mesh. Which means that in the end, based on the new control points, the domain shader creates a more detailed version of the initial mesh without increasing the vertex count in the scene. But what about hair and fur in our scenes? And not to mention the particles that would take a lot of vertices to depict. That is where we introduce the geometry shader, which can take one type of a primitive and make it into something else, which also lets us keep the vertex count low and the performance high. That means that we can take lines to create fur and grass by generating 2 triangles for each line, or a quad with 2 triangles for a particle system based on a vertex. And in the stream output, use the result of all the optional parts to be used in the simulations or collisions, such as the particle systems. Once we are done with all kinds of optional shader parts, we can look at our unit cube or the viewing frustum and clip all the parts that go outside it with face culling to diminish the amount of calculations that need to be done. And finally, we have reached the end, where we can take all that is remaining and transform it to the viewing plane to generate the 2D projection of the 3D geometry in a process called screen mapping, with these transformed vertices having 3 instead of 2 coordinates, including the one for the z depth that we can use later. So we have a lot of substages that deal with vertices and their transformations in one way or another, which also requires a lot of data to compute. Let's say for now that our 36 billion hertz CPU can still handle it. For a set of meshes, we issue separate draw calls, meaning that a higher number of meshes in the scene can require a lot of calculations, which is needed for the next stage, and that is the rasterization stage. Now, given the transformed and projected vertices from the geometry processing stage, our goal is to find all the pixels or picture elements that are inside the triangles being rendered, and we do this through 2 substages, the triangle setup and the triangle traversal. During the stage of triangle setup, we are merely calculating the triangles based on the geometry processing stage, but in the traversal substage, we have to determine which pixel is covered by which triangle. To do this properly, we introduce the quad, or the smallest unit we can work with, which is usually a 2x2 pixel matrix, which we use to calculate the fragments of the image and provide proper color underneath. To avoid having a jagged edge based on the shape of the triangles, we can introduce supersampling anti-aliasing, which takes 16 subpixel samples to determine what color should the edge pixel be, enhancing the overall appearance. However, based on the information from the vertices and the UV maps we had thus far, it can be difficult to generate a render that also corresponds to the changing lighting in the scene, which takes into consideration reflections and global illumination. And that means we have to do some work on the pixel processing, which starts with the pixel shader, another program that can either pass the information about the pixel color down the pipeline or integrate texture and sampler data to provide a new color. Pixel shader can also perform multiple render targets, meaning it can render different colors for pixels based on normals, albedo, specular, and similar, storing them in the geometry buffer or the G buffer. This means that we can render all these targets here, but postpone or defer the lighting calculations to save up on calculations for each mesh we need to do. This approach is called the deferred rendering, and even though it saves time, it has issues showing transparent objects. Finally, we can put all of these passes from the G buffer together along with the Z buffer to know which parts to keep, and then we can get the final result in the output merger substage. So we can see that the amount of information that needs to be calculated here is vast, at least 2 million pixels for an HD display, and with at least 60 frames per second with 4 render targets, we are looking at 500 million operations every second only at this substage. But it seems that the 36 million CPU can still handle it, right? Or are we reaching its limit? So as you can see, there are multiple substages, some mandatory and some optional, that increase the amount of calculations a computer needs to do. So let's see what that number actually is. What would you say the amount of calculations was for a Super Mario 64 on Nintendo 64 back in 1996? Pause the video in the next couple of slides to provide your answers in the comments below. So back in then, it used 100 million calculations per second to display graphics like this. What do you think about Minecraft from 2011? It was nearing 100 billion calculations per second. And we have to mention games that are produced now in 2024, and what do you think their number of calculations is? They require even 36 trillion operations every second, so 1,000 times more than any high-end multi-thread CPU can do. So this is when we have to take into consideration using something that can increase the speed of our calculations and not necessarily the versatility of the tasks that can be done. And this is when we can introduce the graphics processing unit or the GPU inside the graphics cards. So do you know how long the GPUs have been around? So the first consumer graphics chips to include hardware vertex processing, the NVIDIA GeForce 256, was shipped in 1999. However, the Xenox chip was developed around 2004 with a unifier shader architecture, which meant that the shader processing unit of the GPU were shared between the vertex and pixel shading duties. As we mentioned, the shaders are programmable and a primary means by which the GPU is controlled. And if you remember, we have a lot of shaders in the pipeline, and they can all be programmable, with screen mapping and output merger being configurable, while the clipping and the rasterization being fixed when it comes to GPU application. So now we know how the rendering pipeline works. In short, we go from an application stage that deals with collisions, animations, and physics, and then we process all the geometry with the materials to get a better depiction with less calculation time. We rasterize it to convert it to an image for viewing, and in the end, we shade the pixels based on lighting in order to get the final result. Since the pipeline is executed in series, we talked about the possibilities of bottlenecks, slowing down or halting our data flow. And we would like to avoid these bottlenecks for many reasons, but the main one being to improve the performance of our real-time depictions, whether it be games or walkthroughs. By caring about performance, we are basically thinking about optimizing our application to run on target devices smoothly. So if you look at Japan, cleanliness is everyone's responsibility, which is why they have no official janitors in the school or very few trash cans throughout the city. The same can be said for optimization in video games. That is everyone's responsibility. And the way to do it is to use profiling and to do it often. The best way you can do this is by using the stat unit function in the Unreal, for example, that gives you in milliseconds the time that is necessary to generate the frame, calculate the draw calls, game mechanics, and to run the GPU amongst other things. So what does this all mean? So the frame part represents the total time needed to finish each frame. The game has to do with the calculation time, which is necessary for blueprints and C++ gameplay operations. The draw has to do with draw calls, so the instructions the CPU sends to the GPU before the rasterization stage, and the GPU has to do with the amount of time necessary to calculate in parallel all the information in shaders. That means that out of these three, the first two are governed by the CPU, and the last one is obviously governed by the GPU. So if we take a look at this example, what can we notice about the frame time when compared to the other times? We can see that the frame time is not the sum of all the other parts, but is close to the GPU time in this case. This mostly has to do with the game, draw, and GPU all being executed as parallel thread, but with the notion that each thread needs the product of the previous one to run. In this case, the GPU is using up most of the frame rendering time. So when talking about performance, first we talk about the game thread, which is governed by the CPU. Game thread calculates all the game logics and transformations that include animations, object positions, character movement, physics, spawning, and AI. Everything that has to do with the game world around us. And in this case, the bottleneck can occur if we base all these events on tick, which means they are happening on each frame. Now, we don't usually need game scripts happening each frame, since they are event-based. They can happen at certain moments, and they don't have to be updated every frame. Regarding movable objects in the scene, like simple rotations can be done with native logic or the C++ or even shaders, therefore allocating the amount of work from the CPU to the GPU in shaders later on. Some of the really expensive functions in the game thread can be get all actors of class, looping, and spawning. So you can always consider doing all these on tick script in C++. Okay, now we should be knowledgeable enough to know how to optimize performance when it comes to the game thread that is run on the CPU. However, there is another thread that is run on the CPU, and it is called the draw thread. So in order to explain this, we need to remember the final output of the geometry processing, which we use for the rasterization process. In the draw thread, we are considering the frustum culling and object occlusion queries based on the scene depth buffer, but also drawing the meshes onto the screen using draw calls. But what is a draw call? Let's take a look at this simplified version of a scene with a sky, floor, and 3 cylinders, all with different colors in order to try and understand that. So if I were an artist and wanted to depict the scene, I would use my brush, dip it into the blue color, and paint the sky. Then for the floor, do the same thing, dip the brush in green, and paint the floor. And now I can see that I have 3 cylinders that are of the same color. However, I still have to dip my brush each time I want to paint a separate object. So each time I dip my brush to paint one object, we can call that a draw call. It is calculated per mesh, per material. And draw calls have a much greater impact on performance than the polygon count. For example, this 83 million polygon scene with 3,000 draw calls has better performance than a 100K polygon scene with 44K draw calls, especially since every triangle has a different color. So let's take a look at this scene example. And here we can see that each color represents different draw calls, and we can say that 10 to 15,000 objects in the scene is the limit for the optimal performance. But how can we reduce the amount of draw calls? Can we just place all the meshes of the same material together? And that can be useful for reducing the amount of draw calls, but it can be bad for everything else. For example, you have to generate larger light maps if you expect to have any visible detail. Also, you would have problems with occlusion since you take the entire mesh of the building, but you are only looking at the door. The same thing goes for collision. You will have less granularity with large objects when compared to working with smaller models and meshes. And finally, all these things impact the memory usage, given the size of all the models. But what if we use the modular elements? Does using a modular mesh asset help in the matters of reducing draw calls? Technically not, because if you remember, draw calls are calculated per mesh, per material, but we can go ahead and merge all actors or meshes or use instancing to render all the same modular meshes together to optimize the draw call count. However, if we reduce the amount of elements in the object by grouping them based on our proximity to the object, we are observing something that is similar to the LOD or the level of details. And this concept can be improved even more with hierarchical LOD, where you group meshes together based on proximity and your distance from it, also combining their materials into atlases, and all that is 100% non-destructive. However, it can take up a lot of memory, so it should be used with caution. So we can understand that the draw thread has to do with diminishing the amount of draw calls, which are based on the amount of meshes and materials we want to apply. We can use different optimization methods on our own, or software's automatic optimization tools, but still, this does not have that much of an impact as the GPU thread. Now, the GPU has a lot of work to do with the shaders, and hence we can use an additional profiling on it to notice what specific part is causing a bottleneck, which is the profile GPU command. And one of the biggest issues that you can run into here is the overshading part, which means trying to draw multiple triangles over the same pixel when really one pixel can only show a part of the one triangle. This can happen when using a lot of transparent materials like smoke particles or grass elements, as can be seen in this example here. Alongside the overshade, we can also utilize complex shaders, the procedurals that require computing, or texture-based ones that have a larger resolution. And this can cause issues, especially with transparent materials, since the pixel color has to be calculated multiple times for each material that is covering that pixel. Also, one thing we can do to reduce shader complexity is to move the shader calculation from the pixel to the vertex shader if possible. Alongside the shader complexity, we can also take into consideration the light complexity, meaning the amount of overlapping lights that require complex calculations for each pixel. In this scene, we can see how adding additional dynamic or movable lights can increase the lighting complexity and how it can get really bad when you have additional stationary lights as well. So, for example, you can profile your scene which uses fire and a lot of foliage and physics, where if we zoom in, we can notice that the game thread is causing the bottleneck, and then go deeper in uncovering which part in specific is causing this, which turns out to be the blueprints that are happening on tick for a large percentage of the scene. The same goes for this example, where we can profile the GPU thread of our scene and notice what can be causing an issue, which in this case is the base pass, or drawing all of the objects in the scene and rendering them with materials and textures to the screen. So for a scene like this, we can go over and check the shader complexity, for example, and notice that the landscape is taking more time to compute and hence diagnose the bottleneck in our pipeline. So after this entire overview, we should be well versed to not only check under the hood of our real-time applications and diagnose the problem, but also find ways to fix the issue and make it into something better in the same manner Ferruccio did for his car. So next time we can go over the materials within the pipeline and how we can use virtual texturing to optimize the performance. Hopefully you found this extensive review helpful, and if you did, promote the video by liking and sharing, and if you want more content like this, please consider subscribing, as we are hoping to reach our first 1,000 subscribers. I thank you for your time and hope to see you in the next video. Bye.